Remember the discount factor? We talked about it. Yeah. Has discount factor anything to do with the convergence of value iteration? Okay, anyway, people, so how many people think this is true? The smaller the discount factor, the longer it will take the value iteration to converge. How many people think it is true? Yeah, you're actually saying true, right? You're not just...
Yeah.
Okay. Okay, how many people think it's false? Okay, somebody who says it's false, tell me why they think it's false. Yes, go ahead.
Because the sum of the series is I forget, but the denominator is 1 minus the discount factor.
Yeah, any of these questions, by the way, that's a reasonable way of doing things. But any of these questions that I ask, you can answer without formulas. Formulas are important, but as what is actually happening is just as important. Okay. So your answer is that there's something about 1 by 1 minus beta. And that has nothing to do with the number of iterations. So did you think it was something to do with the number of iterations?
Yeah, I thought so. But
So think of the two corner cases. Whenever these kinds of things happen, think of the two extreme cases. Discount factor 1, discount factor 0. Which one do you think will need more iterations before the message comes to you? Remember, there is this whole issue of message. The value iteration is all about the message from the faraway relative who is rich coming to you. Do you see what I'm saying? You can't stop before the message reaches because then you will get wrong answer. So if discount factor equal to 1, what happens? In essence, you have to let the thing play out because even if there is somebody like 2,000 actions away from you who is rich, you have to wait for 2,000 updates and then the value will come to you. Right? What if discount factor equal to 0? Yes, go ahead.
It doesn't care about the future values.
Yeah, it basically doesn't care about neighbors because it knows that it's about to die. Beta equal to 0 means you're dying right now. So, right? So there may well be messages, but they are being attenuated because they're in future. So if you're going to die today, $25 tomorrow is worth 0 for you today. You see what I'm saying? So if the discount factor is low, that is equal to 0, the value iteration will have how many iterations? 1 iteration, basically. Essentially, the 0 iterations. If you just update it, if you set it to be the reward value itself, then it doesn't actually go any further because if you do 1 more iteration, finds that the value hasn't changed, and it stops. Okay, here is a question. So having discount factor close to 0 is being extremely pessimistic about future. You agree? We talked about pessimism and how it makes computation easy. Remember? When was that? A-star search. Set the heuristic to infinity. If you set the heuristic to be infinity, then you'll be done like right away. And you'll say no solution, no solution. You see what I'm saying? Pessimism always makes life short and the computation short. It's the same thing here. Gamma equal to 0 is high pessimism. There is no future. If there is no future, you don't need to think much at all. Value iterations, number of iterations is the thinking cost. You can just sit in a corner and ball because there is no future. But there is no thinking needed. There is no future. You get this? So playing with gamma is actually, in fact, one of the interesting things is that I kind of said this, I showed this last time, I believe. Oh, sorry, I'm going back. Yeah. Remember, I actually didn't mention this. I put it in the notes that the discount factor can be actually interpreted in two different ways, and I use both interpretations in giving you examples. One, of course, is that R t steps away is what beta type or t times R. The other way of interpreting beta is it's the probability. It is related to the probability that the game will end right now. Game ends means life ends. That means horizon is going to be set to that point. So horizon doesn't have to be uniform everywhere. So for you, your horizon is over. Your time is up. So if beta is 0, then the probability that your time is ending is 1 minus 0. Probability 1. That means basically you die. The game is over. So beta is 0 is being extremely pessimistic about future. Okay? Okay. Anything else on these two? Any questions on it? Okay, fine. Let's go forward then. Let's see. So let's just see whether actually maybe I'll come back to this. So discounted MDPs, we basically talked about how to do the discounting such that the sum of the infinite rewards will become finite. And one of the interesting questions, of course, is why the value function converges. In the applet, you saw that the value function is converging, but really the reason that we know that value function will converge is because we can prove a theorem saying that Bellman update is a contraction operator. I'll try to give you a sketch here and I'll give a longer proof on the piazza. So basically, it takes any two vectors. If you apply Bellman update operator, then they come closer. And if you think of one of those vectors to be V star, then in essence, every other vector is being made closer and closer to V star. Because if you take V star and apply Bellman update, V star being the optimal value function, then by definition, Bellman update should give you V star back. Because that's the optimal value. So as you keep applying Bellman update to V and V star side remains as V star. This other guy is coming closer and closer and closer to V star. And in fact, the interesting thing is it comes closer by a factor of gamma or beta. And by the way, this is the other thing. I actually tend to think of discount factor as gamma. In these slides, it's been as beta, but people use either of them. Okay, so it's actually related to the discount factor value. So in particular, you can actually show that BV minus BV dash is less than or equal to beta times V minus V dash. And whenever I say minus for a vector, it's all about norms. You're essentially taking the max norm between the two vectors, the maximum difference between the two vectors. And if you drive down the maximum difference to 0, then they become the same. And every time you are essentially reducing the distance by beta factor. And since beta is less than 1, as long as beta is strictly less than 1, you know that it will converge. How many iterations? That's not guaranteed. In fact, value iteration, there are no bounds as to how many times value iteration has to iterate before it purely converges. Which is why actually policy iteration is interesting. Because in the case of policy iteration, you guys have also read the policy iteration in the textbook, we will talk a little bit. In the case of policy iteration, at least there are only a power s number of s power a number of policies. Number of states power number of actions. So if you just keep track of the duplicates, you'll at least know how not to look at the same policy more than once. Value functions are real vectors, real valued vectors. There are infinite number of them. Okay? Okay, so then there in just like so in addition to let's get back to the policy evaluation. Okay, first let's talk about the policy evaluation. So even though we are actually interested in computing the optimal policy, which is the value iteration, you also want to understand that given a policy pi, you can evaluate it. Remember, that's exactly what we did for finite horizon. First we evaluated the policy, then we did optimal policy. Okay? Now the interesting thing here is and I said that in the finite horizon case, evaluating the policy essentially involves solving a set of simultaneous equations of a very simple kind, where some equations are essentially saying x equal to 1, y equal to 2, etc. Another equation is saying x plus z equal to 3. Since you already know the value of x, you can compute the value of z. In the case of infinite horizon, essentially you just solve this particular set of equations. So value with respect to policy pi of some state s is, of course, the reward for that state s plus beta times the probability of, if you know the value, the policy pi tells you what action to do in s. Let's call that pi of s. Let's say a. So if you do action A in state S, you will get to state S dash with some probability. And that S dash has a value with respect to this policy. So there are S number of states, so there are S number of variables, each for the value of each of the states. And you get a set of simultaneous equations in S simultaneous equations in S unknowns. And you can solve them. In fact, computing, solving a simultaneous equations essentially is matrix inversion. Even though that's not the way you did it when you did it last time around. In linear algebra, you heard that solving simultaneous equation is just matrix inversion. Matrix inversion is a polynomial time operation. Okay? So that's computing the value of a policy. So computing optimal policy, you basically don't get this nice thing. Here you essentially had a simple linear equation. It's very important to understand that underneath that, if you actually plug in the numbers, they are just a set of linear equations, with the variables being v of s. Right? Okay? Now, if you're doing the optimal value function, then what you need to do is basically, this is the true Bellman equation, which just says v star of s is r of s, and this part is the same, except for each action A, you have to compute this sum. For each action A that you could do, what is the expected value from the neighbors that you are getting? And you take a max over all the actions. You didn't have to do the max before because the policy told you which action to do, and that's the only action you did. Here the policy isn't there, so you have to consider every action that you can take. And you then wind up saying, I'll take the one that's the best. It's easy enough to say, except all of these are unknowns. V star of every state is an unknown. So now you have S unknowns, S simultaneous equations, except these equations are not linear. They're non-linear because there is a max operation sitting right smack dab in the middle. Okay? And the value iteration essentially is just thinking of this, and instead of saying equal, it's just basically looking at it as an assignment and making it iterations. So let's start by initializing all the values to the rewards. That will be V0. That's the first iteration. And in the second iteration, everybody essentially uses this computation to update their values. Instead of using it as equality, you just use it as an update. Okay? And you keep doing this. Every time you do this, you have changed your value once more. And after some number of times of doing this, if your value hasn't changed between two iterations, then your value has converged. And of course, the entire value function is a vector over S states. And you would say that the value function itself has converged if between two iterations, the maximum difference between the two value functions in the two iterations is less than epsilon. Okay? That's what basically value function is doing. Okay. So this max operator makes the system nonlinear, so the problem is more difficult than the policy evaluation. And then the optimal value function is a fixed point of this Bellman backup, which is this particular thing being used as an update. Okay? Where the update essentially is this. Bellman update of a value function V essentially does this by looking at its neighbor's value. So that's one iteration of value function, value iteration. So this will be a new value function. And you're essentially saying the value function that you get by doing B of V would be closer to V star than the original value function. And one of the interesting things is this is true of all fixed point computations. Really, it doesn't matter what you initialize the value function with. I kind of said, let's do it the way we did for finite horizon value iteration, which is to put reward function values, right? But I can put all zeros. And if you think for 3 seconds, you'll realize that if you start with all zeros, after one iteration, they'll all become reward values. You see this? Right, because the second part is 0, the first part is R of S. So after one iteration, it's become R of S. This is also the place where if your rich uncle says, yeah, I don't know the true value, but I have some kind of a hint for you. Here are some numbers, throw these in and see if you can reduce the number of iterations. So that is, if I can give you an approximation, to V star, that's better than 0 or R of S, then the number of iterations will reduce even further. What does that sound like? Heuristic. That's exactly what, if you want to understand A star search as a Markov-Decision process, the heuristic is the initialization of the value function. Sort of. Okay? So that's another way you can improve the speed of the number of iterations that you have to do. One last thing is, if you're into general computer science, and if I asked you, is the value iteration, an optimal policy computation, is it exponential or polynomial? Is it tractable or not for Markov-Decision processes? That's a reasonable question to ask. You know that sorting is tractable. Its n log n algorithms are there. So is value computation tractable or not? Actually, until now, whatever I said doesn't tell you that it's tractable at all. Because value iteration, number of iterations that value iteration will go to, if you do it as an update, is infinite. You don't know exactly how long it will continue doing before the value is driven down to less than epsilon. You can only put some bounds, but they're not very strong bounds. And if you think in terms of policy iteration, it's still exponential. Because if you do the brute force search of looking at each policy and comparing it to the next policy, right, which is one way of doing it, right? Because now I know how to evaluate a policy using this. And there are only S power A number of policies. I throw in each of the policies into this equation, I'll get the V pi for that. I compare them, take them optimum. Again, remember, you should always understand the thumb way of doing it so that you can appreciate the better way of doing it. But if you're doing this, clearly it's like n factorial way for sorting, and it still tells you that it's intractable. Normally the way you show that something is tractable is what? You actually show an algorithm and say, look, this algorithm solves it and it has polynomial complexity, so the problem is tractable. I haven't given you yet an algorithm that is polynomial times. Right? I'm hoping that it seems to work mostly, but I never gave you an algorithm which is polynomial. It turns out that actually you could take these and write these directly as an integer, as a linear programming problem. How many of you have heard of linear programming? Okay, so linear programming essentially is actually one of the reasons why this guy called this idea dynamic programming. Linear programming is if you have a set of linear constraints on a set of variables, and you have some linear objective on those variables, then what should be the values? So for example, if I have, suppose, let's see, if I have x1 plus 3x2 less than or equal to 5, x2 minus 5x3 less than or equal to 7, etc. These kinds of constraints, and I want to say maximize 4x plus 7x3 minus 2x2. That's linear programming problem. Have you ever seen this in your life? In fact, I know for sure that those of you who went to schools here, you have seen it at the time when you saw finite mathematics in your middle school end or beginning of the high school. Without having seen this, you would have even gotten into calculus. Okay? Turns out that the linear programming problem is actually polynomial time solvable. That in itself is actually a huge big secret. For the longest time, people didn't know whether linear programming is tractable or not. Until a guy called Karmarkar, Narendra Karmarkar, showed an idea called interior point algorithm, and showed that its the complexity of that way of solving linear programming is actually polynomial. So now we know that linear programming is polynomial complexity. And I just told you that you can compute optimal value as a linear program. And so you have a way of proving that there is a polynomial time algorithm. Nobody actually uses that particular algorithm other than to show that it's polynomial time. Because you notice that there can be huge constants, and so runtime complexity might actually be worse for the so-called polynomial time algorithm. But it's worth remembering that optimal policy computation is polynomial in the number of states, for Markov-Decision processes. That's the last you will have that luxury. Once you go to POM-DPs, partially observable Markov-Decision processes, that's not true. It becomes exponential for finite horizon and undecidable for infinite horizon. Okay. Okay, so let's just see if I can tell you what, this is basically what I was saying about the convergence proof. I mentioned this multiple times, but I want to show you some intuition as to why this actually works out, why updating, the Bellman update drives down the distance between the two vectors. And so this is the minimum you can understand, and then maybe I'll walk you through a longer proof outside of the class, either on a piazza or one of the videos. So essentially, if you look at this, B of V, Bellman update on V for state S is this. B of V dash is this. You can subtract one from the other. You get B of V minus B of V dash of S is this. Up to this is just normal algebra. Yes?
just to make sure I understand it properly, so this practical is the traveling salesman form of the, like, not practical?
If you do not have a polynomial time algorithm, it's not practical.
Okay.
Okay. And so then basically, so you have, you got this up to here. And now what I do is I'll say this is less than this. First magic. Now that to understand that, you only need to understand this general property of any function f on g. If you have any function f on g, the max of f minus max of g over all a's. That means every point, if you consider all the points in of the range of the function, of the domain of the function, okay? So here is f and here is g. Where is max of f over all x's? Here. Where is max of g over all x's? Here. If you subtract this from this, you'll get that much. This can be shown to be less than or equal to the maximum difference at any given point between both the functions. In this carefully constructed example, you can actually see that, right? Because this is the maximum difference between, so this is maximum difference between these two functions is this. For the same value x, this is g of x, this is f of x. Did you just see what I just said? So I'm just saying this is less than or equal to this. I use that to essentially say this is less than or equal to this. Where essentially I have functions in a more complex form. And once I do that, from that and another couple of facts, one of which is this, which is for any function, in fact, you can think of that as functions. I wrote in terms of v's, but you can think of f. In any function f and g, f of x minus g of x is less than or equal to max of f of x minus g of x. Obvious, right? So basically I'm taking, for any x, I'm taking the value between f and g, and the difference between f and g there will have to be less than the maximum difference that they can ever have. That's pretty obvious. By the way, many of these theorems go like this. They will take pretty obvious things, like subset superset connection. I actually made a lot of comments on the A-star search notes that subset superset and how the minima change over them is connected to A-star search proof. And that's what we're doing. It's another of those numerical properties, another of those simple properties we're using here. If you use that, and the other fact that you have to notice is that this is a probability distribution. PSAS dash is a probability distribution. So if you, for any given A, PSAS dash over all S dash will have to sum to 1. So if I say, what is TSAS dash times K? Where I'm going over all S dash. K is a constant. It is just K. You see this, right? I'm multiplying K by a whole bunch of numbers which add up to 1, and I'm summing them up. So I'll get K back. You use that, those two, then you'll get the next part, which is that this is basically less than or equal to beta times Vs minus B dash x. That's it. That's the contraction property. Which basically means every time you do a Bellman update, V and V dash are coming closer and closer. Now if you think of one of those V dash to be V star, then B of V star is just V star. That means every time you do a Bellman update on V, it's coming closer and closer to V star. And this doesn't matter as to where you started with V. Beautiful proof. This is why initialization doesn't matter. Okay? So that's the proof stage of contraction property. And then if I were to compute using value iteration, the optimal value function, then I need to then convert it into the policy. Right? How do I do that? I do the same thing that I did for finite horizon. So if I know V star, I can always convert it into the action I'm supposed to do. So if I know, if I'm in state S dash, I'm state S and I have a bunch of neighbors around me and I know all of their optimal values, then for each action I can take, I can compute what is the expected backup for that action. And I will take the action that has the maximum expected backup. You see what I'm saying? I said this for finite horizon, and I also said for the finite horizon that you may as well remember at each stage which action was it that gave you the max. And that way you don't have to recompute this. You see what I'm saying? You could do that too here. In fact, there is a different way of doing this here. If you don't want to, after getting the optimal value, if you don't want to do this for each action, the probability that that action takes to S dash times V star of S dash and expected value backup for action A, and then compare all those numbers. If you don't want to do that, instead of actually computing the optimal value function, you could compute what is called the optimal Q function. And it so happens that V star of S is max over A of Q star SA. So instead of just remembering one value number for each state, I will remember if from this state I do action A, then what is the best long-term outcome I can get? This is called the Q value with respect to this action A. So instead of tracking one value function, one number per state, you are now tracking A times S numbers, S times A numbers. Right? For each state, I need to know the Q value for each of the actions. And if you do that, at the end, you don't need to do any additional computation. You right away know max Q value tells you the action with the max Q value is the optimal action for that state. Now, this is actually, some of you may have heard of an idea called Q learning. How many have heard of Q learning? Okay, and the fact that AlphaGo used deep Q networks. That's the Q. And we will talk about Q learning in